Hello class! So this lesson is 4.1, Gravitational Force Near Earth. Now, you already know something about gravity. It's what makes things fall towards the Earth. I want you to imagine a situation where you've got two pieces of paper. One flat piece of paper that you're holding horizontally, and another one that's crumpled up. And if you drop them both at the exact same time, the question is, which piece of paper will reach the ground first? You'd probably guess that it is the crumpled paper. But to understand why, we need to understand something called air resistance. So first, I want to explain the concept of freefall. Freefall is when a falling object only experiences gravity and no other forces. Now this is not very common. Usually, when you have something falling, it has wind going against it, and it creates something called air resistance. So air resistance is a force that prevents falling objects from falling. Right? It resists that falling motion. And it depends on two factors. Those are, number one, the cross-sectional area of the object. And that's how large it is when you view it from the top, how wide across it is. So the flat paper had a much larger cross-sectional area. That means that more wind can hit it. And the second thing that matters is the speed of the object. So the faster something is going, the more air resistance it experiences. And that's important because what happens is, as something falls, it gets faster and faster, but the air resistance gets larger and larger. So eventually that air resistance ends up balancing the gravity, and you reach this point where they're perfectly balanced and it doesn't speed up anymore. That's called the terminal speed. So this is the maximum speed of a falling object. We're going to look at that in the context of a skydiver. So down here, we have a few boxes, and I want to draw free body diagrams in each one of these boxes. It's going to be our skydiver, and what's happening to our skydiver. So at the start, we have our skydiver, and when they just jump out of the plane, well, our skydiver is going to be experiencing gravity downwards, and maybe a bit of air resistance going up, something like this. But as that skydiver has been falling for a while, well, he's going to be experiencing the exact same amount of gravity, but he's going to pick up some speed, so it means that he's going to experience more air resistance. And as he gets even faster, eventually that air resistance gets so large that it is perfectly balanced with gravity, and it means that he's not accelerating anymore. If the air resistance is equal to gravity, that means our net force is going to equal 0, which means that we're not accelerating and we hit our terminal speed. Now, if we keep on going, if you've ever seen somebody skydiving, what happens is eventually you open a parachute. Now, when you open the parachute, all of a sudden your cross-sectional area gets much, much larger, right? These parachutes are very wide, and that's the whole reason we have parachutes. So still, I'm experiencing the exact same force due to gravity, But all of a sudden, I've increased my cross-sectional area quite a bit, which means my air resistance shoots way up. And you'll see now that the air resistance is much larger than gravity, which means I'm going to start slowing down. I'm going to start accelerating upwards, which means I'm going to slow down. Now, after I've slowed down for a bit, well, as I get slower, my air resistance gets smaller. So this guy is going to be not quite as big. And eventually, it's going to drop down enough that it's once again perfectly balanced with gravity, which means I'm not going to change speed anymore. I'm not accelerating. The air resistance stays constant. The gravity stays constant. My net force is equal to 0. And again, I'm at terminal speed. And this new terminal speed, with my larger cross-sectional area, is slower than above, than the last time that we had terminal speed. Now, we can see this also in the equation for drag force. Air resistance is a type of drag force. There are other drag forces, and we have a general equation down here for all drag forces. You do not need to know this equation, okay? You do not need to know it. I'm just showing it so that you can see where this speed and cross-sectional area comes in. You can see the equation is Fd equals 1/2 times rho, which is density. We're not talking about it right now, but times v squared. V is our speed. So you can see that as v gets larger, the drag force will get larger. And then times cd, the drag coefficient, which again we're not looking at, but then times a, our cross-sectional area. So you can see how those two factors are important in determining drag force. Great. Now that's it for air resistance. We're going to pop on to the next page here, which is about a new topic, the gravitational field strength. So first off, gravitational field strength, an important idea is this idea of a force field. I'm not talking about Star Wars here with force fields that deflect lasers and that sort of thing. A force field is a real thing, and what it is, it's a region of space where objects experience a force. So all around Earth, objects experience a force due to gravity. That is a gravitational field. It's a force field. So we can talk about force fields in that sense. Our gravitational field, we want to be able to describe this. And we can use something called the gravitational field strength, which is the force per kilogram that an object experiences in a gravitational field. Okay, so for every kilogram that I weigh, or that I have, it tells me how much force I will experience because of those kilograms. Now, our variable is called g, lowercase g, and it equals Fg over m. And yes, this is the exact same g that we've been seeing before, our 9.8 meters per second squared g. That describes how much force we experience. So when I say g is 9.8, it means that for every kilogram, it's going to experience 1 newton of, it's going to experience 9.8 newtons of force for each kilogram. So in general, we can describe this g as Fg over m, and our units here are newtons per kilogram. Now you might say, well, I know g is 9.8 meters per second squared. Yes, but we can also call it 9.8 newtons per kilogram. the units come out the same. You might remember that newtons are kilogram meter per second squared. So when you divide that by kilograms, you get meters per second squared. Now, when we're talking about g this way, we want to describe it as newtons per kilogram because we're talking about how much force each kilogram experiences. But really, it is the same thing as the 9.8 meters per second squared. So g is not always 9.8. It really depends how far away from Earth you are. So right here in Toronto, we have a g of 9.807 newtons per kilogram. If you were to climb up a mountain, it would get smaller. And if you go really far up, in this case 6,371 kilometers up, you would have a g of 2.45 newtons per kilogram. And I chose that distance, 6,371, because that's the radius of Earth. So if I go from the center of Earth out to the outside, that is 6,371 kilometers. And what I'm saying is if you go that same distance again above the Earth, well, g becomes much smaller, 2.45 newtons per kilogram. So that shows you that the further you get away from Earth, the more it sort of drops off. And it drops off actually with the square of that distance. Okay. That's gravitational field strength. Now to the right we have another picture here, 2 Canadian astronauts on the International Space Station. And they look like they're just floating there. We talked a bit about this before. The idea that on the International Space Station, it looks like people are floating. It looks like they don't have any weight, but they actually do. They actually have very close to the same amount of weight as you and I do here on Earth. So why does it look like they're floating? Well, to answer that, we need to look at this idea of mass versus weight. So to begin with, mass, this is an important idea here, this distinction here. So mass is the quantity of matter in an object. So related to its actual particles. Like this is a real measure of how much matter there is, how much stuff there is. That's the mass. Whereas the weight is the force of gravity acting on an object. And that changes. Mass never changes. When you have an object that's 10 kilograms, it's 10 kilograms here, it's 10 kilograms in outer space. It doesn't matter where you are. Whereas weight, it changes. If I am here on Earth, I might weigh one amount. And if I go up to the International Space Station, I'll weigh less. If I go up to the moon, I'll weigh even less. Because there's less force due to gravity in each of those places. If I go out in outer space, I pretty much weigh nothing, because there's no gravity acting on me. So that's how you can feel like you weigh less if you have less gravity acting on you. Now, still, on the International Space Station, they experience a very similar amount of gravity than we do. They are operating at a g of 8.69 newtons per kilogram, which is not far off from our 9.81. So again, why is it that they're floating? Well, it's this idea of weightlessness or microgravity, where they really do have weight, but this idea of weightlessness is when no normal force is holding you up. Holding you up. Okay, so it's the normal force that makes us feel like we weigh something. If you jump out of an airplane, if you go skydiving, you'll feel weightless. If you go on the drop zone at Canada's Wonderland, or that sort of a ride, a roller coaster that goes really fast down, well, you'll feel weightless because you don't have any normal force holding you up. You're going to be under freefall, which feels weightless. So I'll say, for instance, drop zone. when you're under free fall. When you're free falling, you don't have any normal force and it feels like you're weightless. That's actually what's happening on the International Space Station. They are constantly free falling. It's kind of funny to think about, but if I draw them above the Earth here, what they're doing is they're orbiting around like this. And they're orbiting, they're constantly falling towards the Earth, but they're falling in a way that they actually rotate around the Earth. And that's something that you won't learn about really until grade 12. But the idea is they are actually falling towards the Earth in a circle. And that circle keeps them perfectly the same distance from the Earth the whole time. So that they're constantly falling, but they're not actually changing how high above the Earth they are. And so that's why they feel weightless. So they're only 400 kilometers above Earth, above the Earth's surface. But they are, they seem weightless because of free fall, because they're constantly free falling towards the Earth. Okay. So that's this idea of weightlessness, and the idea that normal force is an important concept to determine how heavy something feels. Okay. Now, last page here, we're going to do a few problems to show different situations where the normal force is not always equal to gravity. Our first problem says a cart rolls down an incline. Assume that friction is negligible. Draw a free body diagram for the cart, and in which directions do the normal force and the force of gravity act on the cart. I'll draw an incline here, and a cart on the incline, and it's moving in this direction, right? It's falling down the hill. Now, if I was to draw the same thing as a free body diagram, it's going to have gravity acting straight down on it. Gravity always acts straight down, whereas the normal force is always perpendicular to the surface. In this case, our surface is going down to the right, so our normal force is perpendicular to it, so it's pointing up something like this. That's our normal force. Now, our normal force doesn't perfectly balance out gravity. You can see that if I add those two up, well, the vertical components are going to cancel out a bit, but I'm going to get a net force going in this direction. This is going to be my net force when I add those two together. And that's why I end up accelerating down the hill. Okay. We'll look at the next problem here. It says a 50-kilogram person is standing on a bathroom scale inside an elevator. The scale is calibrated in newtons. What is the reading on the scale when the elevator is accelerating up at 2.2 meters per second squared? Again, I'll draw a free body diagram. And this person has a force due to gravity. We know what that is. Fg is equal to mg. Okay. We can work with that. Now, they also have a normal force acting up on them, and they're accelerating upwards. So that means that this normal force must be larger than gravity. And we know that our net force, F net, that's equal to ma, which in this case, our mass is 50, and our acceleration is 2.2. So that gives me a net force of, just a moment here, gives me a net force of 50 times 2.2. It's going to be 110 newtons. Okay, great. So that's my net force. Now, if I want to figure out the reading on the bathroom scale, my bathroom scale tells me how much normal force I'm experiencing. So I want to find out the normal force here. I know that the net force is also going to equal normal force acting upwards minus the gravitational force acting downwards. Okay, so we can say 110 newtons, that's equal to my normal force minus mg, which is 50 times 9.8. So if I want to then solve for normal force, we have normal force is equal to 110 plus 50 times 9.8. And the end result there gives me a normal force of 600 newtons. And there we go. That tells us what the reading on the bathroom scale would be. Great. We'll look at the very last problem here, and then we're done. It says a 60 kilogram person is standing on a bathroom scale calibrated in newtons again. A friend pushes down on the person with 72 newtons. What is the reading on the scale? So if I draw my free body diagram again, this person is experiencing the force due to gravity, and they're also experiencing this applied force now from their friend of 72.0 newtons. So if I want to find out the normal force here, well, this person isn't going up or going down. They're standing perfectly still on this bathroom scale. So it means that the normal force has to balance those others out. So we've got F net equals 0, which is equal to my normal force minus Fg minus 72.0 newtons. So that tells me that Fn, that's equal to my gravitational force mg plus 72.0 newtons. And mg, I can rewrite that as 60 times 9.8 plus 72. And that's going to give me a total force here of 660 newtons. And there we go. That's the reading on the bathroom scale. So hopefully that makes sense how we can measure our normal force these different ways. And one of the important ideas is that normal force is what we're measuring when we use a bathroom scale. Great. Thank you very much. Have a good day.